In this video, we check for outliers in linear regression using STATA. We have previous episodes where we've checked for all the assumptions 1 to 4, including how to check for multicollinearity using variance inflation factors. You may need to check them out. So when running and interpreting a linear regression analysis, it is important to check for outliers. Outliers are simply out-of-range values that may distort the outcomes of our analysis, giving us misleading conclusions. And in linear regression, there are three ways how you can test for outliers in your dataset. One is using leverage points. We can also use Cook's distance, and we use a difference in betas called DFBETAs. Let us have a simple understanding of each of these concepts to lay a foundations for us during interpretation of the values. To understand leverage points, let us consider a simple plot of an outcome plotted against the values of a predictor. We have points with a small x in yellow that shows data points ranging between 0 to 10, where majority of them are falling for your independent variable. If you fit a line of best fit for those points, that is the yellow dotted line. However, we also see that there is another point or an observation of the independent variable that lies far beyond the usual or where majority of the points are lying. For it, it is at 20 here. And if you consider that observation in your analysis, it gives you the bold red line, showing you that the line of best fit with that point shifts upwards. So that point X there in red is what we call a leverage point. So a leverage point simply measures how far an independent variable's value for a given observation is from the mean of that variable, indicating potential to influence the regression model. Most of the participants lie between 0 to 10, but that one observation is far away from where it is expected or far from the crowd in terms of the predictor. So that's the leverage point. It can shift your regression point, meaning it shifts your standard errors, it shifts your p-value and the confidence intervals. You may come up with conclusions that this variable is statistically significant or not, which is actually not right. So we need to check for those outliers. We have what we call Cook's distance. Similar to what we've just seen in leverage points, we have Cook's distance. We have a line of best fit, considering the points in yellow and considering the red point, which is quite unusual. So Cook's distance is a measure of how the entire regression model would change if one observation is removed. When the observation is still there, we see that the line of best fit is up here. If that point is removed, then we see that the regression line shifts to the one dotted in yellow below. So for it, it combines the residual size or the outcome unusualness and the leverage or the predictor unusualness. And the question you're asking yourself here is, if I kick this person out, does my regression line change a lot? And here, if we have values above 1, they indicate a potential outlier. So you need to go back to your data set and have a second look at that observation. Is it really truly entered correctly, or there might be an issue with it? And lastly, we have difference in betas, which show how much a specific regression coefficient changes if we remove a particular observation. And values above 0.5, those are potential outliers. So on this background, we are going to get these values. We are going to get the leverage points, Cook's distance, and DFBETAs, so that we analyze and determine whether we have outliers. Here is our hypothetical data set that we are going to use to demonstrate how to check for outliers. We have blood pressure, our outcome, and two independent variables. So to test for outliers, we have to first fit that model. Then we use estimates from that model. So to fit the linear regression model, we are going to statistics, linear models and related. Then we go to linear regression. In this dialog box, specify your outcome, which is blood pressure, and then the independent variables. Here we have age and BMI. Then we click OK. Here is our output from STATA for linear regression. We are not interpreting this right now, but we wanted to first fit the model so that we are able to get the statistics that we can use to check whether they are outliers. To get the leverage and Cook's distance, we shall go to statistics, post estimation, then we go to predictions, then we go to predictions and their standard errors. We have here several predictions that we can produce from that model that we've just fit. But for now, we want Cook's distance, and it is going to create a new variable. So we can just call it Cook's distance, and I click submit. So you can see there is a new variable created here, which we shall see shortly. But we also want leverage values produced. So we are going to check leverage and then change here the name, leverage. Then you click OK. You can now close this. You can see that I have now a variable Cook's distance and leverage, which you can browse here and see. We have Cook's distance and leverage. So what we can do with these are to get summaries of these variables to see whether there is any which violates the assumption. So we shall go to statistics, summaries, tables, and descriptives. Then we shall get summary statistics. We are interested in getting summary statistics for Cook's distance and leverage. Okay. Yeah, so I would ask for display additional characteristics, then click OK. So here you have the summary statistics for each of the variables, Cook's distance and leverage. Actually, I can just remove that detail here, and it just gives me, I'm interested in the minimum value and the maximum value within that variable. For leverage points, we are interested in values below 0.5. If we have any value above 0.5, that is a potential outlier. We look at the summary. The maximum point for leverage is 0.15, meaning all variables, all the points are below 0.5. So we do not have outliers. Even when we look at Cook's distance, the maximum is 0.13. And for Cook's distance, any value above 1 suggests a potential confounder. But the other side, we saw it was the maximum was 0.13. So using Cook's distance, the assumption has also passed. Lastly, we can look at the DFBETAs. For you to get DFBETAs, simply go to statistics, linear models and related. Then you are going to choose regression diagnostics, and then you will see the difference in betas is here. STATA can create for you difference in betas for all the variables if you leave this empty. Since we have two variables, here we can leave it empty, and then we click OK. Then you will see that we have DFBETA1, DFBETA2, the one for age, and BMI. They are also created as new variables. df beta 1 and df beta 2. So we also need to summarize these variables to see which one are the minimum and maximum values. I can just pick a command here, summarize, and I just change these. I remove them and I put these two variables. You can see that the maximum df beta for age is 0.28 and the other one for BMI is 0.37. And for df betas, we are also interested in seeing values below 0.5. So even using df betas, our assumption has been fulfilled. If you found this video useful, consider liking and subscribing to the channel so that you don't miss out any of our episodes. So this has been the last video on checking for assumptions of linear regression. We've checked for linearity, independence, normality, equivariance, and yeah. So next we shall go to another step of linear regression, which is choosing variables to include into your multiple linear regression model. See you in the next episode.